right, great, everyone. So let's start. So today we're going to talk about model-based RL, and we're going to talk about a new setting, which is called generative model. So here we're going to do data-driven approach. We're going to learn something from data, and then we're going to compute optimal policy. Right. So this is kind of the first algorithm that is using data-driven approach to compute the optimal policy. All right. So before we jump into the recap, let me just quickly mention something about the homework. So I think some of you were complaining that the derivation for the LQR is very tedious. I think it is, but when you do the derivation, you can actually simplify terms a lot and make them a very succinct expression at the end, right? And these derivations are tedious, but I think you're all interested in reinforcement learning, so I think doing the derivation for LQR once in your life is actually worth to do it. And if you ask all these like control theorists or control practitioners, if you ask them what's the first optimal control approach that they learned or they derived or they programmed, right? It's very likely they're going to tell you that this is LQR, right? So I think the homework basically forces you to do derivation in a very old-fashioned way, a pencil, a piece of paperwork, and you just write down these equations, right? So I think it's a good exercise, and I think everyone should do this very carefully. Yeah, and of course, if you're running into problems or doing derivations, come to the office hour and ask us, right? All right, so let's do some quick recap. So we're gonna move back to the Markov decision process, but hopefully at this stage you've already convinced yourself that LQR is just a special case of Markov decision process, right? Except that in MDP we often talk about maximizing reward, and in control setting we often talk about minimize the cost. Yeah, so we're gonna move back to the infinite horizon Markov decision process in this lecture. Let me just quickly remind you what this setting is. So we have state space, action space, transition probability P, and reward function R, and we have a discount factor. Okay, sorry about that. My Apple Pencil is not working. Okay, let me retry it again. Sorry about that. All right, okay, let's continue. All right, so we have this infinite horizon Markov decision process, and we have this important discount factor. And a policy is a mapping that maps from state to action, right? And we talked about Bellman equation, and which is very important, and we use that for design algorithms for policy evaluation, right? And then along the way, we talked about Bellman optimality. So these are the properties for the optimal policy pi star, right? So in the first homework, we proved this equation, and in the class, we talked about the corresponding Bellman optimality condition for the value function V star. Right, so these are the key, two key properties of Markov decision process, right? And we use these two properties to design two algorithms, right? The first one is the policy evaluation, where we treat this Bellman equation as a fixed point iteration, and we design an algorithm that iteratively, find an estimator that converges to V pi. And similarly, we designed this algorithm called value iteration, which is this one, right? So if you still remember this equation, so if you span out, if you write this value iteration in your code, so you do for all SA, right? So you keep updating your Q estimation using this expression, right? So you're treating Q star as the fixed point solution of the Bellman optimality, right? And then you keep repeating. You do fixed point iteration algorithm. And what we explained in the lecture is that this Qt will converge to Q star at the rate of gamma to the power of t. And then we talked about policy iteration, right? So policy iteration basically says that every iteration I have a policy in hand. Let me just use policy evaluation to compute its Q function. So this is the Q value, the Q function of the current policy, pi t, right? And then let's just design a new policy to be the greedy operator with respect to the current policy's Q value. Right? And we prove a monotonic improvement in a sense that Q pi t plus 1 for all SA is at least as good as Q pi t SA, right, for all SA. And in the current homework problem, you're asked to prove that if you hit a point where you cannot find any improvement, right, then we want to prove that at this point we already converged to an optimal policy. Right? So in other words, we keep doing hill climbing. At some point we cannot find any local improvement, then we're guaranteed that we find an optimal policy. So this algorithm returns the optimal policy pi star with finite number of iterations. And this algorithm is approximate algorithm, right? Right. So another concept, I hope at this stage you already had a much better understanding on this concept due to the first homework. So we talked about this state action probability, right, distribution. Right. So let me just remind you what it is. So it is basically the exponential average over the state action distribution at each time step. Right. So this term is basically says what's the probability of visiting a particular state action pair SA at time step h if we start from the fixed initial state as 0 and following policy pi, right? And the average one is just the exponential average. Right? So that's basically the quick recap. Any questions so far? Okay, so we're going to talk about a new setting. So this setting is slightly more general than the setting that we've been talking about. So the setting that we have been talking about, the setting that we used in value iteration, policy iteration, this dynamic programming, for tabular MDP and LQR, right? So we all assumed that this P and R, they are known, right? So in other words, we know this probability for all SAS prime, right? So this is given as the input of our algorithm or input of our program, right? Similarly for LQR, what we assumed is that this A matrix plus B matrix, even plus the noise, right? We assume that both A and B are known, and we assume that this noise is from some known, for instance, Gaussian distribution, right? So this is also known. So in other words, even in LQR, I tell you everything about this transition probability, right? Because P of X prime, XU is nothing but just a Gaussian distribution. Right? So I know the mean and the variance of the Gaussian distribution. So that means that I know this distribution, right? Right, so there was no learning or data-driven approach involved in the previous lectures, right? Okay, so now we're going to slightly relax the assumption that we know everything. Okay, so we're only going to assume that we have general model setting in this generative model setting, in the sense that we can reset the system to a particular state action pair, but we can only get a sample from this distribution. Right, so we don't know what's going on inside this black box, but what we can ask is that if I set the system to state S and action A, the system returns a sample from this conditional distribution, right? But we don't know the probability. We only observe in a sample. So think about, you have a biased coin, right? You flip a coin, you only observe the outcome, but you don't observe, the probability, the bias of the coin, right? And we can estimate that later on, but, we have to do some extra work to estimate that probability, right? Now, this is definitely a weaker assumption than the non-setting, right? Because we need to get samples to estimate these probabilities in this P table, right? And this is a valid assumption, for some problems. For instance, for board games, right? You can actually reset to a state action pair and observe what's the next state, right? And the next state might depend on the strategy of your opponent. But you can actually reset it there and ask your opponent to provide a next move, right? Then you observe the next board position. And for control and planning simulation, yes, we can definitely do that, right? Because it's a simulator. So we just set the simulator to a state action pair, let it do the process in the black box, and then observe the next state. Right? So this is kind of what we were doing in the homework programming problem, right? So we never told you, the explicit analytical form of the cost function and the transition dynamics of the catapult, right? All you have is set it to a state action pair, observe the next state, and then you do some sort of finite differencing or whatever, to get an estimation of the model, right? Now, this assumption is still a little bit strong, right? Ideally, we do not want to assume this resetability, right? But we will get rid of this assumption in the next few lectures. So in other words, we start from a very strong assumption, assuming everything's known, right? Assuming that we understand the word very well and how we do planning if we understand the word very well, right? But now here we get to some sort of middle ground where we only assume that we can reset, but afterwards you have to do estimation, all right? And eventually we're going to get into a situation where we get rid of this resetability assumption. Right, so reset is sometimes a very strong assumption, right? For instance, if you're going to assume resetability for instance, autonomous driving, so this is kind of saying that you can reset the car to a situation where, for instance, the car is running at this particular speed at this particular location, with two particular pedestrians walking in front of the car with that particular velocity, right? So that's pretty strong assumption. You cannot really reset to that kind of situation that easily, at least, right? And especially in the real world, you cannot really reset to this kind of situation, right? So we have to sort of drive the car around and we hope to run into this kind of situation, right? But we can't reset, right? But we will get to that settings later on. All right, any questions about this new setting?
On this one, are we assuming that we already know R or no?
Yeah, so for simplicity, we're gonna assume R is no. Okay, but you can, if you see the algorithm later on, we will talk about how to deal with the setting, how to deal with the setting where R is not known, right? So usually R is much easier to estimate. All right, so of course, the question for today then is that under this generative model setting, how we can learn to compute pi star. Right, so this is probably going to be an approximation algorithm. We're going to find a policy pi that is maybe epsilon close to pi star, right? And what performance guarantee that we can get, right? And particularly, we're going to see the first sample complexity example, sample complexity analysis. So in other words, this says that if I want, an epsilon optimal policy. How many samples that I need to collect? Right, so this is usually the question of the sample complexity question. Right, so you specified a precision, you want an absolute optimal policy, and then we hope that the theorem or the algorithm tells us that how many samples you need to collect, right? And if you satisfy this number or total number of samples, then I guarantee the algorithm guarantee you that it will find an at least absolute optimal policy. So that's sort of the guarantee that we want to have for this algorithm. Okay, so outline for today. We're going to start from a very general result, which is called simulation lemma. So in other words, this lemma is concerning the following questions. So if I have an estimator of P, right? So this P hat is estimating P. So in other words, P hat might be approximately equals to P, but not exactly the same. There might be some error, right? We spend a lot of effort, building an estimator, but there might be some sort of difference between our estimator and the true world, right? So what's the performance of a policy pi under this estimator, right? How does the error in the model in the P hat propagate back to the performance of a policy, right? Imagine that we have a simulator that's a self-driving car simulator, and we have a driving policy. So we want to basically ask ourselves, if I test this driving policy in the simulator, and I tested the driving policy in the real world, what would be the difference between these two values, right? In other words, if there was an epsilon gap between my simulator and the real world, I want to get an understanding how this epsilon is, how this error is amplified when I'm actually translated to the performance of that policy. And so this lemma actually tells you this amplification. And then with this lemma, we're going to just talk about very simple algorithm. We're just going to estimate this model P hat from data. And then with that model, we're just going to do, for instance, the policy iteration algorithm on the model P hat and compute an estimate policy pi hat. And then for analyzing the performance, we're just going to ask ourselves, what's the performance of this policy pi hat star under the true system, right? So remember pi hat star. For instance, this is the output of policy iteration under our estimator, right? But we care about the performance of the policy pi hat star under the true model P, right? So this is what we care. So we're just going to ask, we're just going to use simulation lemma to compute this gap, this performance gap, this performance, right? So motivation for model-based approach. This is a very common and a default approach you actually try in practice, right? So this is like this model-based approach. This is basically this fundamental approach that we use for instance, landing robots on Mars, right? So one example is that in this simulation that I showed you before, this is actually achieved by a model-based approach, right? So in other words, in high level, while we cannot write out the exact analytic formulation for this robot, for instance, right? But we can, ask the robot to generate a bunch of data in the format of state, action, next state tuples, right? And with that, we can do estimation. For instance, we can do something like least square, right? Sum over I equal to 1 to n, f s a minus s prime, L to norm, mean over f, right? So if the state is in a Euclidean space, right? We can also do maximum likelihood estimation. We can do mean max p hat, right? Sum over I equal to 1 to n. Let's just write out the log likelihood, for instance, right? P hat s prime s a. Right, so the first equation, the first optimization is least square. The second optimization is maximum likelihood estimation. So you can use this kind of approach to learn, to learn this dynamics or this transition model P using the data that you collected. Right. So assume that the model that you learned is pretty good, then we can actually just use it for planning, right? For instance, we can do value iteration, use the learned model, or we can just do policy iteration using the learned model as well. Right, so that's the usual framework for model-based RL. So it's called model-based because we first use data-driven approach to learn a model, right? And then we do planning. And we know how to do planning at this stage, right? We have value iteration, we have policy iteration, and even for continuous stuff, we have dynamic programming, we have LQR. And often in practice, we're going to iterate the above process, right? In other words, once I get this policy, pi hat, let me just execute that policy in the real world and get more data, right? And with more data, let's just refit our estimation. And hopefully now its estimation gets slightly better. And then let's redo the planning process. And then let's repeat over and over again and until it converged. Right? So in other words, if you're trying to do model-based RL for self-driving car, you start from a reasonably good simulator, right? You compute a policy using the simulator. And now today you're just going to send your car on the roads using the learned policy. And at the same time, you're collecting a bunch of data, right? Data about how pedestrians walking, data about how the other cars are driving around, right? And then with that collected data, at night, you can refine your simulator, right? Once you refine your simulator, and then you can recompute a policy. And then on the second day, you can drive the car out again using the new policy, right? So on and so forth. So hopefully, gradually you build a better and a better simulator. And under the assumption that planning is actually doing its own job, then your learned policy will actually be better and better. Right. So that's the hope of this general model-based approach. Right. So any questions so far? All right. So then
I have a question.
Mhm.
So I guess when you're collecting SA and S prime, right, you have to use one policy.
Yeah.
Right. So the trajectory that you get, it's actually dependent on the policy that you use initially.
Mm-hmm.
Isn't that that actually can lead to the possibility of like if you use a bad policy at the beginning and it will just sort of like lead you to like a series of trajectory and some of the space or dynamics being unexplored?
Yeah, totally. Yeah. So I'm not saying anything about the optimality of this procedure, right? So this is a practical approach you're going to use, but in general, it's not going to give you any performance guarantee. So as you said, you very easily get into some local minimum, right? Because there's no exploration around, right? So you kind of just hoping that this algorithm converges to some local minimum solution, local optimal solution, right? But there's no global guarantee. Right?
Okay.
Yeah. Because there was no exploration, right? So once we get to the exploration part of the lecture, we can revisit this problem.
Okay.
Right.
Thank you.
Yeah, so this is actually the fundamental problem of reinforcement learning, right? So this is the fundamental difference between reinforcement learning and supervised learning. So in other words, here, we needed to get data by ourselves, right? And then we fit a model using the data that we collected, right? But when we test our policy in the real world, the state that you're going to encounter in the future, they might not be different. They might be different from the state that you collected, right? Because your policy hopefully improved. So, there's a training and testing distribution mismatch in RL, right? But in supervised learning, there's no such kind of difference, right? You train a model on this distribution and you're testing the model under the same distribution. But here, RL, like even you do this one iteration, you get this distribution mismatch, right? Because your policy or your model is trained under the old data set, but now you're driving the car using the computed policy, right? And the policy might start visiting different kind of state. So at this stage, your performance, you don't really get any guarantee on the performance, right? Because this is like, you haven't even seen these kind of data sets. So how can you guarantee that your yesterday's estimated model is good enough, right? So there's this distribution shift, right? That's why RAO is much harder than the traditional supervised learning, right? Because we have to deal with this distribution shift. Right, but for today's lecture and next Tuesday's lecture, we're not going to worry about this problem, right? Because we're going to do some assumptions to first get rid of this problem. You will see in a few seconds. All right, so let's just talk about this fundamental problem, right? So let's formalize two notations. So this v hat pi is the expected total reward of my policy pi under my estimator p hat. Right, so this is like, if I executing this policy pi in my estimator p hat, what's the expected total performance, right? And of course, we have this true v pi, which is the expected total reward of the policy under the true system, right? And we care about the difference between these two, right? V hat pi S0 minus v pi S0. We care about this. And particularly, we want to get a formulation such that this arrow can be quantified by the difference between these two models, right? Maybe there is a function f. Maybe there's a formulation, right, that looks at the difference between p hat and p and tells me that, how big the difference would be for this v hat and v pi. V hat pi and v pi, right? That's our hope. So if you can get this formulation that basically says that now, if I understand the error of my model, I can compute an upper bound of the performance difference, right? So that's great. If I get a good understanding of my simulator's error, then without driving the car in the real world, I basically get a good sense of the performance of my policy, right? By just testing it on the simulator. Right? So in other words, yes, we care about the difference between these two values. And in other words, how does the model error propagate to the values, right? So remember, these values and the policies, they're the true quantities, they're the ultimate quantities that we care about, right? Like estimating a model is a way for us to get a good policy. So this is the simulation lemma, right? So this looks a bit complicated, but let's pause for a second and try to pass each terms. All right, so the left-hand side is just the difference that we care about, right? Let's ignore about the 1 over 1 minus gamma term. So you can imagine, you can guess where this is coming from, right? This is coming from this gamma plus gamma squared plus gamma cube and so on and so forth, right? And the expectation says that we are only focusing on the state action distribution of the policy at the true transition P, right? So this is the distribution of pi under the true model P, right? So this is the definition that we did in recap. And under this distribution, we are sort of measuring the difference between P hat and P, right? So think about this quantity as the difference between P hat and P for now, right? So this is like, you have two distributions. If you have distribution P and distribution Q, right? And one way to compute the difference between them is compute the expectation of x over P, fx minus expectation Q, x over Q, fx. Maybe for all f, right? So if the two distributions are the same, then this quantity is going to be 0. Right? If the two distributions are very different, then measured under this f, their error might be big. Right? Think about this as some quantity that measures the difference between p hat and p. Right? It's just averaged over this function f hat, v hat. All right, we're going to revisit this point later on, but just so far, just think about this simulation lemma. Basically, it tells us that the difference between the quantities that we care about is sort of the average model disagreement, right? Averaged over the state action distribution induced under the true system. Right, so let's think about how we actually can, explain or prove this, right? So we can start thinking about this from the graphical model perspective, right? So we have a policy pi and we have a transition p hat, right? So this defines a Markov graphical model, right? For instance, I have state S translated to S prime. I have action A here. And this is like one segment of my graphical model, right? So this is pi AS. And this is S prime is from P hat SA. Right? So this is a graphical model, right? This is a Markovian graphical model. And then I have another one, right? Which corresponds to the true model. They're almost identical, except this state transition. Right. So basically, I'm comparing against two Markovian chain, right? Because the action distribution is the same. They're executing the same policy, right? It's just that they're transit, based on two different probability matrices, right? P and P hat. Right. So we can draw the same picture that we had when we were talking about the policy performance difference. So we start from S0, and let's say this is the trajectory that if I follow policy pi under P hat. Right, so these are my waypoints. And this is the trajectory if I follow pi under P. Right, so these two trajectories could be widely different because they're following different transition probability, right? The first one is under P hat, the second one is under P. Right? And as we argued, directly computing the difference between these two widely different segments is probably very hard, right? So the common trick that we do is introduce some middle ground. And in this case, we're going to introduce this middle ground. So this says that let me first follow pi and P for one step. Oops, sorry. Right? And then I'm going to switch to another strategy, which is pi and P hat. So it's like, let me step in the real world for one step, and then let me just roll out in the simulator. Right? So this is the middle ground that we can introduce. So similarly, let's 1, 2, 3. So we cared about the difference between 1 and 3. So now this is 1 minus 2 plus 2 minus 3. Right? And for this term, as you can guess now, we can just gonna do recursion. Right? Because 2 minus 3 is the difference between these two new segments, right? So this is basically the same situation that we faced when we were at S0. And 1 minus 2 is actually a term that looks very similar to this term, right? So what does this term say? This term says that, there's another color. So the first term says that I'm always following policy pi under P hat, right? So this corresponds to segment 1. And the second term says that let me first follow P, right? The true model. Let me first step in the true model. And then I switch to my estimator P hat, because this is V hat, right? V hat means that I'm executing policy in the estimator P hat. So this actually corresponds to trajectory 2, right? Because we take one step in our real model, and then we immediately switch to our estimator P hat. Right? So in other words, 1 minus 2 is actually a term, they're going to appear in the final expression, right? It's just that 1 minus 2 is the term that corresponding to time step actually equal to 0. Right? But when you do one-step recursion on the term 2 minus 3, you're going to get another term at the next time step, so on and so forth. And then you average them together, you get the expression you want. Right? So that's the high-level idea. And with that picture in mind, the derivation is actually pretty simple. Right? So we just start from the quantity that we care about. Let's just cancel out the common reward function, right? Because both of them, they're going to follow the Bellman equation, right? Because these are valid value function. It's accepted that they are indifferent Markov decision process, right? Let me just write one more step. So this, you can write this as R S0 pi S0 plus gamma expectation of S prime from P hat, right? Remember, this is the value of the policy pi inside the model P hat. So that's why I'm using P hat here, right? So we're doing everything in simulation, right? S0 pi S0, right? And V hat pi S prime, right? So this is a Bellman equation applied in the model P hat. Right? You can do the same thing for this V pi, right? It's just the Bellman equation applied in a different Markov transition, which is P, right? All right, so they share the same one-step reward. You cancel them together, and you get back to this equation, right? All right, so just follow what we did in the previous slides. Let's just introduce some middle ground. I'm just minus and add a particular term, right? So this is like, care about the difference between these true trajectories. I introduce this middle ground. This is 2, 1, 3, right? So this term is 2. Right? I just introduced this middle ground. Now I'm doing like something like 1 minus 2 plus 2 minus 3. Right? So if you just rearrange in terms, I'm not gonna go into the details of this. So this term corresponds to 2 minus 3. This term corresponds to 1 minus 2. Right? So 2 minus 3, we can start doing recursion because this quantity is mirroring this quantity, right? Except that we moved one step forward. Right? And as we argued, 1 minus 2 is actually a term that is going to appear in the final expression. Right? So look at this term. It's a different color. So if you look at this term and this term, right, they are almost the same, except that the term inside the derivation is concerned at time step 0. Right? But if we do one more recursion on the term 2 minus 3, we're gonna get a similar expression, but this time it will be concerned at time step actually equal to 1. Right? And we do one more recursion, we get a term that is related to time step actually equal to 2, and so on and so forth. And then we average them together, we get back to the expression, the final expression in the lemma, right? So this is just averaging over different time steps, right? Remember the definition of this d pi s 0. This is just exponential averaging over all the time steps. All right, so that's basically the derivation. I think the detail of the derivation is not super important if you somehow get a bit lost during the derivation, right? So I think you can offline, you can just sit down and redo this derivation by yourself. I think you'll quickly get it, what's going on. But the high level of this simulation lemma, again, I think that's the most important key, right? So the high level is that we want to quantify the difference between a particular policy, executed or measured under two different Markov decision process, right? One is P hat, one is P. And we want to quantify the performance difference using the difference in the models, using the difference between P hat and P to quantify the difference between the policy's values under these two systems. Right, so we can do one more step up bound. We can basically turn this term, which I previously said this is sort of quantifying the difference between p hat and p, right? We can upper bound it using L1 norm or total variation distance between p hat and p. Right? So what I used is for two distributions p and q, expectation x over p of fx minus expectation so q is less than the L1 norm between q and p, which is 1 over 2 of the total variation distance between these two distributions. Sorry, this times sup x of fx. Okay, that's all the inequality that I use. And here we get an amplification on the horizon because our v hat pi is ranging between 0 and 1 minus 1 minus gamma, right? Because our reward is bounded from 0 and 1. So my value function could be as large as 1 over 1 minus gamma. All right, so now the expression is very clear, right? So this says that I can actually bound the difference of the policy executing under the two systems just by the disagreement, the total model disagreement measured under total variation distance over the real traces, meaning the trajectories that are generated by following the policy pi under the real model p. Right? Remember, this is the state action distribution of the policy pi induced at the real system p. Right? So picture-wise, we start from S0. We just follow policy pi under p, right? Under our real system. And then along this waypoint, right, let's check the model disagreement. Let's check the model difference. Maybe at this waypoint, my model will say you're actually going to go here. And maybe at this waypoint, the model is going to see that you're going to go here. Maybe at this point, it's going to be say here. It's going to see here, right? So let's just calculate the model disagreement along these waypoints generated by pi under the real model p, and then average them together. Right? So that's basically what simulation lemma is telling us. Now, this is pretty remarkable, right? In a sense that this quantity could be the difference between two completely non-overlapping trajectories, right? But somehow, after these derivations, we are saying that to bound the difference between these two non-overlapping trajectories, we just needed to look at the model disagreement on the waypoints on a trajectory that is generated by pi under the true model p. Right? But of course, we pay some amplification, which is 1 over 1 minus gamma squared. Okay, so this is particularly nice because we can actually just bound the difference between these two values, the policy values, by looking at the model disagreement, on the trajectories that you're going to generate in the real system. Right? So in other words, you can drive your car in the real world, right? Along these waypoints, you just compute the difference between your model and the ground truth model. Right? And then you can basically get an upper bound on the performance difference.
Does the left-hand side of the inequality not have absolute value at the end?
You can add absolute value. So this still holds.
Okay.
Yeah.
Okay.
Because you can just switch the order, right? So
right.
if you switch the order of these two terms, you're going to switch these two orders, right?
Right.
And the other absolute value, they're the same, right?
Okay. Thanks.
What does the SUP mean again? Sorry. And that expectation.
Oh, you mean this d pi as 0?
Like on the right hand side of that inequality.
The sup.
Yeah, what does that mean? The SUP
On
the bottom of the page.
He's asking supremum.
Oh. This is max over, like the maximum value. Sorry.
Okay.
the maximum value of this function.
Oh, okay.
Right.
Thank you.
I have a question.
Yes.
So I noticed that you're using stochastic pi in the previous proof. Are we switching to using stochastic policy now?
Do I
Or
use? Oh yeah. So okay. Oh yeah. So I forgot to mention at the very beginning. So at this stage, I want you to gradually sort of start thinking about the stochastic policy. Right. So we didn't do that because I didn't want to introduce extra burden during the first months of this course. But now you can actually gradually start thinking about stochastic policy. Right. So deterministic policy is just a special case of stochastic policy, right? Because you just put all the probability mass on a particular action. But of course, you can do stochastic policy, and you just take the expectation with respect to the stochasticity from the policy. Right? But this whole thing also holds for deterministic policy, because deterministic policy is just a special case of stochastic policy, right? All right, so that's the simulation lemma, and we will see how we can actually use that for analyzing the algorithm. Right, so any questions so far? So this is one of the very important results in reinforcement learning. Right, and this lemma we should actually fully understand and master it, because this is a very fundamental thing, right? So it's just telling us like if I have some error in my simulator, right? I want to see how the error is propagated to the value of a policy. Right, so any questions so far? So understanding this lemma is required, right? So next we're gonna move to some analysis, and there are some steps in the analysis is optional. So I will mention that, but like we should absolutely master this lemma, right? This is one of the very, very important results in reinforcement learning. All right, so that's basically the first part. And now we're just going to talk about the algorithm. And if we have time, let's just quickly analyze it, right? But as I said, this step is important, and this analysis is, we can be a little bit sloppy here, right?
I guess a quick question.
Yeah.
Like in practice, it seems difficult to evaluate kind of the D distribution, right? But I guess since it's an expectation, you can basically like upper bound the difference and still be okay, right?
Yeah, or you just sample, you just execute a pi in the real world. Just drive your car around, get samples, right? Because you can estimate the expectation by averaging over samples.
I see, like Monte Carlo. Okay.
Yeah.
Great, thanks.
All right, so the algorithm is very simple. So we're going to use the generative model assumption. And here we're only going to care about small MDPs, in a sense, discrete MDPs. Right? So what we're going to do is, let's just first do model fitting. For every state action pair, let me collect n next state. Right, so I'm at state action pair, maybe with probability 0.5, I will transit to S1. Maybe with probability 0.2, I will transit S2. And with the rest of the probability, which is 0.3, I transit to S3, right? So this is my distribution, but this is hidden, right? But we can draw n samples from SA, right? And then use these samples to make an estimation, right? So this quantity is saying that the p hat at SA, S prime, is just the ratio between two numbers, right? The numerator is the total number of times I hit S prime. And the denominator is the total number of samples, right? So the ratio between these two numbers is basically approximating the probability of hitting a particular next state S prime. Right, so I do this for every state action pair. So now I get this estimated p hat. All right, and then I just do policy iteration on this p hat. That's the algorithm. right? So our hope is that p hat S prime over SA converge to P when n approaches to infinite, right? So intuitively, this kind of makes sense because, think about the law of large number, right? So if I get infinite data, then of course this ratio is going to approach to the true probability, right? If I flip a coin, infinite many times, then I can estimate the bias of the coin very accurately, right? Right, so that's the algorithm. And any questions about the algorithm? Yeah, here we are using the assumption of the generative model. Right, so in other words, we reset to a particular state action pair, we generate many next state. Right, and our hope is that we use these samples to estimate the probabilities of this unknown p. Right, we just do counting. How many times we have hit a particular next state S prime, right? And the probability estimation is just the ratio between this number of hitting times over the total number of samples. Right, so to analyze that, the first step we're going to do is let's just ask the question, right? How accurate p hat is comparing to p? Can we quantify the difference between p hat and p using the number of samples n, right? Right? For instance, we care about the L1 distance or the total variation distance between two distributions. Can we say something about the difference between these two using the parameter n, for instance? Right? And intuitively, we expect that the difference between these two models goes to 0 when n approaches to infinite. And then the last step is very simple, right? We just use simulation lemma to propagate the model error to the performance of our estimate policy, pi hat star, right? So pi hat star is the optimal policy under our estimate p hat, right? Because we run policy iteration inside p hat. So this is an optimal policy of our estimator, but this is not necessarily a good policy under the real system, right? We have to ask ourselves how good it is if we execute in the real system P. So simulation lemma is going to tell us this. Okay, so before we dive into the details, let's just take a detour, right? So let's just ask ourselves, how can we estimate, the mean of a Bernoulli distribution? So I've been talking about, flipping the coin many times so far, right? So how can we actually estimate the bias of a biased coin? So in other words, I have a coin, with probability p. If I flip it, it will give me the positive side, +1. And with the rest of probability 1 minus p, if I flip it, it will give me the negative side, right? -1. So I don't know the p, right? And I want to estimate p. So what we can do is let's do experiments, right? Let's just flip the coin n times independently. We get n outcomes, right? So these outcomes are written as xi, where xi is a random variable that is either -1 or +1, right? So I just do n experiments. I just flip coin independently n times. I record down, if it's positive or it's negative, right? So how can we estimate a p? Right? Very simple. Let's just do counting, right? So p corresponds to the probability of getting a positive phase. So that means that we can estimate p by just counting how many times in these experiments we have observed the positive side, right? So the numerator is saying that how many times you hit +1. And the denominator is the total number of experiments, right? So this is the ratio of how many times we hit the positive side over the total number of experiments that we have done. Right, so by law of large number, p hat should converge to p if n approaches to infinite, right? right? If we do infinite many experiments, eventually this quantity is going to tell us the true P, right? Because if you do infinite many experiments, the sort of you gradually converge to the underlying probability P, right?
Sorry, I think I missed something, but when you're doing these experiments, do you just randomly pick an action to transition to the next state, or
okay, so here there's no transition. It's just a coin.
but like you're trying to calculate the probability that you go from state S to S prime, right? And that's dependent on some action, right? So how do you pick the...
Yes. So let's worry about that question in the next slide. Here, let's just focus on estimating this coin, right?
Okay.
It's not related about RL or transition, whatever. I just give you a biased coin. I'm asking you, give me an estimation, right? So this is the approach you will do. You're just gonna flip them n times, and you're gonna return me this ratio, right? Let's worry about the RL setting in the next slide. Right, so this law of large number, this kind of thing tells us this asymptotic performance, right? In the sense that if I do infinite many experiments, I know that P hat will converge to P, right? But what if n is finite? Can we see anything when n is finite, right? So in fact, we can have such kind of nice result, right? So the proof is out of scope, and this is often called a concentration bound, in a sense that we sort of care about how fast our estimate P hat is concentrating to the true probability P. All right, so I think the details doesn't really matter here. This is telling me that I can actually build a confidence interval for my estimator. So this is my confidence interval. So this middle ground will be my estimated P hat. And this upper bound will be P hat plus square root of log 1 over delta over n. And this bottom side will be P hat minus log 1 over delta over n. And this result is telling you that somewhere inside this interval is our ground truth P. So we know that P actually falls into this confidence interval. We don't know where it is, but we know that this confidence interval contains the thing that we care about, P. Right? So this actually matched to our intuition, right? When n approaches to infinite, confidence interval is going to collapse into a point, right? When n equal to infinite, the upper bound, the lower bound, they were going to collapse into a point. So at this stage, we know that, P must be approaching to the middle point, P hat, right? When the interval collapses. So this is just telling you a particular rate of convergence. Right? In other words, if you do n experiments, roughly the distance between your estimator and the ground truth is roughly upper bounded by 1 square root of 1 over n. Right? I don't want to get into the details of this high probability 1 minus delta thing, but just think about, the deviation is sort of decreasing in the rate of 1 over square root of n. So if you do 100 experiments, the difference is roughly like 1 over 10. You can do like thousands or 10,000 of experiments, right? Then you get a sense of how far away your estimator is comparing to the true one by just calculating this square root of 1 over n. Right, so this is a very classic result in probability and statistics, right? Because we truly care about these kind of quantities, right? Like we do random experiments, we get some estimation. We really care about how far this estimation is from the ground truth, right? And this kind of concentration result is telling us this bound, right? So now I can see more than just this law of large number, right? So I can basically say that for any number of experiments, n, I can give you a confidence interval, and I can tell you that your ground truth P will actually falls into this confidence interval, right? I don't know where it is again, but I know that it's inside this interval. So, the proof of this is out of scope. I just want to give you a, sort of a sense of how this confidence interval, what this confidence interval thing is, right? And we're not going to really sort of dive into the details of this. And if you're interested in this kind of thing, you could actually take the 6,000 level class next semester, where we're actually going to use these kind of results for analyzing reinforcement learning algorithms. But here, I think it's a good, I'm not requiring anyone to understand the proof of this kind of inequality, right? But it's a useful tool that we should be aware of, right? Like if one day we want to build a confidence interval for our estimation, we know that there are such kind of results exist in statistics, right? Now we actually know a more advanced tool than the law of large number, right? Previously, we only know that, when the number of experiments goes to infinite, our thing will converge to the ground truth. But now you actually can build a confidence interval for any arbitrary number of experiments, right? And you can tell the user or whatever, your ground truth will fall into my confidence interval. All right, so let's get back to the model fitting, right? So here we are literally just doing trying to estimate the probability, right? So this basically says that at SA, with probability P S prime SA, we will get S prime, right? When we sample the next state with probability P S prime given SA, we can actually hit S prime, right? And with probability 1 minus P S prime given SA, we observe something else, right? It could be some other random state, but it's not S prime, right? So if this is like, you're trying to estimating the bias of a coin, right? Because here you flip a coin, you're going to see S prime with this particular probability. And with the rest of the probability, you're going to see the rest states, right? The rest of states that is not equal to S prime. All right, so in order to estimate this bias, this probability, we just do counting and then compute the ratio. All right, so if you use the previous result, you can see that P hat S prime given SA minus P S prime given SA, it will be something like 1 over n, right? Let's ignore about the log terms and constants, right? And this means that total variation distance, or L1 distance of the two distribution at SA, this is sum over S prime in S right? And using this simple calculation, we basically say that the total variation distance between P hat and P at the particular state action pair is upper bounded by the number of states S times this convergence rate, which is square root of 1 over n, right? So now this is good because by doing n experiments, we roughly get a sense of the deviation between our estimated P hat and the ground truth P, right? We don't know where P is, the ground truth is, but we know that it's not that far away from our estimator, right? Okay, so in fact, you can do much better by moving the factor S inside the square root, right? Again, this is out of scope. I'm just, stating this result. But I think the key sort of message is that this still grows 1 over square root of n, right? So this is square root S over n. Remember the naive calculation we just did? We had S outside of the square root, right? But if you do a very refined analysis, you can actually put the S inside the square root, right? But we're not going to touch that. But the important thing is that, again, as n approaches to infinite, this deviation is diminished in the rate of square root of 1 over n, right? All right, so summary so far, we are just dealing with the model estimation part, right? And what we get is some sort of confidence ball measured in the L1 null for our estimate, right? So again, ignoring this high probability statement, I mean, I put there because this is sort of the true statement, right? But let's not worry about these details. So we have, basically we build a confidence ball, right? The center is our estimator, right? And the radius of this ball is this square root s over n. Again, ignoring log factors and the constant, right? We're gonna be stopping on constants and log factors, right? And we know that somewhere inside this ball, we have this ground truth P SA. We don't know where it is. We only know that it's inside this ball with that particular radius, right? And the radius shrinks as we do more experiments. Right? So any questions about the model fitting part? Right? Yeah. So just remember this picture, right? We have a confidence interval whose center is our estimator, and we have some radius whose length is shrinking in the order of 1 over square root n. And somewhere inside this ball, we have our ground truth P, right? And the distance is measured under this L1 norm. This is the L1 norm, right? Okay, so let's just calculate the ultimate quantity that we care about, right? Remember, the second step of this algorithm is actually do policy iteration under the learned model P hat, right? So we get the optimal policy for P hat because we run value iteration, right? We know value iteration going to hit an optimal policy, but it's just this optimal policy happened to be the optimal policy of our estimator, right? But we care about its performance when we execute it in the real model P. Right? So in other words, we care about the difference between V star and the performance of our estimator pi hat star, right? Right, so let's just do this trick, right? So minus a term, I immediately plus a similar term, not exactly the same term back, right? And I claim that this is, the inequality is this direction. And let's think about why this is true, right? Someone want to give it a try? Notice the difference between these two terms, right? And let me remind you that V hat pi is the performance of pi under the model P hat.
Is this our lemma?
Is what?
Is this the lemma we proved earlier? Or?
No. We haven't got to that step. That lemma is going to be the next step, right? So here I just add a term and a minus a term, and I'm claiming that this is. So basically, I'm claiming this term is positive, is not negative.
Is this because the performance of pi hat star under P hat will be better than like pi star under P hat?
Yes,
because, yeah.
Exactly. Yeah. So remember, we do policy iteration, right? So pi hat star is optimal under hat P, right? But pi star is not necessarily an optimal policy under hat P, right? So in other words, if I measure the performance under hat P or P hat, right? V hat pi star hat must be bigger than any other policy's performance, including pi star, right? Because V hat pi star is just the optimal one under P hat, right? It should be dominating other policies. So that's why this term is non-negative, right? Yeah, so this is great. We use the optimality condition of our estimate policy, pi hat star. All right, so now you can actually do simulation, right? Simulation lemma. So this looks like complicated, but all we're doing is just apply simulation lemma on the first term and apply simulation lemma on the second term, right? So recall the simulation lemma. Simulation lemma says that for a particular policy, pi, what's the difference between their values when I'm evaluating them under two different Markov decision process, right? So the first term here says that I care about the performance of pi star under these two models. And the second term says that I care about this pi hat star under this two Markov decision process, right? So let's apply simulation lemma twice, one for each term. And this is the line that we're going to get. Right, so I simulation lemma twice, okay?
Doesn't the simulation lemma require the same policy?
Yes, so here it is the same policy, right?
Yeah.
So look at the first term, it is pi star. Look at the second term, it is pi hat star, right? They are the same policy. It's just they're evaluating under different system, right? All right. So we know how bad these two quantities could be, right? So we calculate this. This is like S over n. This is like S over n, right? So if you just combine them together, we get a term look like that, right? So that's basically the end. The first step, use the optimality, at pi star under at p, right? And the second step here is simulation lemma. And the last step, use the confidence interval. The confidence bore result that I told you, right? All right, so that's great because now if we do n experiments, the difference between the policy's performance and the optimal policy's performance is diminution in the rate of 1 over n, square root of 1 over n as well, right? So this is kind of expected. If you do more samples, our model will be more accurate and our policy will gradually have better and better performance comparing to the optimal policy. Right, so let's turn this into the sample complexity, right? So let's just do it. It's very quick. So let's see, we want to get a particular precision. I want to make sure that my outputted policy is at least epsilon, is at most epsilon away from the optimal policy, right? So then we can just set n to be this number. And then the previous result will basically guarantee that the performance is at most epsilon. Right? So remember from the previous slides, we had this. Right? So if we care about, if we can only tolerate epsilon approximation error, so let's just set this term to be epsilon, right? And we solve for n, so n is s epsilon square 1 minus gamma to the fourth, right? And remember, n is the number of experiments that we do for each state action pair. So we have total s many state action pairs. So the total number of samples is SA times n, which is S square A over epsilon square 1 minus gamma to the fourth. Right, so that's the sample complexity result, right? So this says that you specified a threshold, right? So you only can tolerate the epsilon approximation. And I, as the algorithm designer, I will tell you that, hey, you should go ahead to collect that amount of samples. And then you run my algorithm, it will guarantee you to find a policy that is at most epsilon away from the ground truth one. All right, so that's basically the end. And the key ingredients here is the confidence bore construction, which let's just take it as is, right? Just trust me that this is correct. And then we do the simulation lemma. But here, the simulation lemma is a more fundamental stuff. Well, I mean, the confidence bore is definitely fundamental. This is very fundamental stuff in statistics. But I think let's just take the confidence ball construction as is, and let's try to definitely understand the simulation lemma for sure. Yep. Right, so that's basically the end. And a quick summary. We designed a very simple algorithm that using counting, right, to estimate p hat. We just do experiments n times, count how many times we hit a particular next state, and then we compute the ratio, right? And then the algorithm is just to do policy iteration under this model p hat. And then we talked about simulation lemma, and we use simulation lemma to get this final result, right? Together with the the given confidence ball construction. Right, so that's the end of today's lecture.